What happens when a bullet's components aren't manufactured correctly? Catastrophic failure. That's why ammunition factories have such rigorous quality control systems in place. Today, we're getting unprecedented access inside these facilities to show you the 4 parallel production lines that must work in perfect sync. Each line faces unique challenges and requires precise timing. What could possibly go wrong if even one line lags behind the others? You'll never look at ammunition the same way again after seeing the intricate steps required to produce just one round. Don't forget to like this video and subscribe to our channel for more behind-the-scenes access and in-depth insights. Ever wonder why bullets look so simple but cost so much? Let's take a peek inside one of the world's most precise manufacturing operations. Welcome to the bullet production line, where raw metals transform into meticulously crafted projectiles through a fascinating blend of engineering and metallurgy. When you hold a bullet, you're holding a carefully balanced compromise, like a finely tuned scale where every gram matters. It needs the right weight to maintain momentum when fired, while being perfectly shaped to slice through air with minimal resistance. Getting this balance right determines whether you hit your target or waste your shot. The journey begins with material selection. The factory sources specific lead alloys for cores, providing the crucial density that helps bullets maintain their trajectory. Surrounding this core, copper forms protective jackets that prevent barrel fouling and enhance durability as the bullet spins through the barrel at incredible speeds. For specialized applications, you'll sometimes spot more exotic materials like steel or tungsten when extra hardness is needed, particularly in military-grade ammunition. Next, witness how automated presses transform these raw materials into precision-engineered cores. For most consumer ammunition, cold forming dominates the production line. The process is mesmerizing. Machines grab lead wire, cut precise lengths, and compress it into bullet shapes through a series of dies. These setups produce thousands of bullet cores hourly with remarkable consistency. Look at those craftsmen working with specialty equipment. They're creating competition-grade bullets through casting, offering greater control for precision shooting. Molten lead gets carefully poured into precision molds designed for specific bullet geometries. Once cooled, these cast bullets undergo additional finishing to meet exacting standards that competitive shooters demand. The jacketing process adds another layer of complexity. Copper sheets are rolled to precise thicknesses before being cut into circular blanks. These blanks transform into cup shapes that eventually envelop the lead cores. The operation demands immense pressure and precise tooling to create perfectly uniform jackets. Check out how engineers constantly test every aspect of the bullets. Even tiny variations in weight distribution affect accuracy dramatically. When a bullet fires, it spins rapidly due to the rifling in the gun barrel. If the weight isn't perfectly balanced around its center axis, the bullet wobbles in flight, something shooters call precession, sending it off target. That room filled with computer workstations? It's where modern bullet design happens. Engineers use advanced simulation software to model aerodynamic performance before creating physical prototypes. These simulations account for everything from air resistance to gravitational effects, allowing designers to optimize bullet performance for specific applications. The production floor uses specialized measurement tools to verify each bullet meets these computer-generated specifications. Micrometers, precision scales, and optical comparators constantly check dimensions, ensuring physical bullets match their virtual designs within incredibly tight tolerances, often just thousandths of an inch difference between perfect and unusable. Now that we've seen how bullets take shape, let's move to another fascinating part of the factory. Those small brass cylinders you might have seen on the ground at a shooting range. They're actually engineering marvels that perform an incredible balancing act. Think about what a cartridge case does. It's essentially a pressure vessel designed to survive an explosion. When fired, it expands to seal the chamber against escaping gases, then shrinks back just enough to be extracted. These remarkable containers can actually be reused multiple times, unlike most vessels built to withstand explosions. In this section of the factory, we're watching brass cases take shape on a parallel production line. These components handle pressures up to 50,000 pounds per square inch, enough to destroy most everyday objects, while remaining flexible enough to extract without breaking. The process begins with simple sheets of brass. Similar to how a potter transforms clay, these machines mold flat brass through a process called drawing. Transfer presses move the metal through a series of dies, each one progressively reshaping it. Watch as the flat brass first becomes a shallow cup, then with each step grows deeper and more refined, transforming from a flat disc into a precisely engineered vessel. It's like watching a magician pull an impossibly long object from a small space. Just as a signature authenticates artwork, the head stamp certifies each case. Look at those markings being applied to the bottom. A powerful press stamps information about the manufacturer and caliber. These markings help shooters identify their ammunition and prevent dangerous mix-ups. Connected to this identification is one of the most precise operations happening right here: flash hole drilling. This tiny channel serves as the vital pathway for ignition. When you pull the trigger, the firing pin hits the primer, creating a small flame that travels through this flash hole to ignite the main powder charge. Perfect drilling ensures reliable firing every time. Now check out one of the most fascinating steps: annealing. Here, metallurgy transforms into something almost magical. The neck and mouth of each case need to be softer than the base, so workers carefully heat only those specific areas. Annealing requires absolute temperature control. Too cool and the metal won't soften properly. Too hot and the case loses structural integrity. Specialized equipment heats just the neck and mouth areas to precise temperatures while leaving the base strong and hard. This process combines heat and metal in ways that demand stringent safety protocols. The factory employs specialized ventilation systems and heat-resistant equipment throughout this area. Workers undergo special training and follow strict procedures to maintain safety standards. During final production, each case gets meticulously measured. Even slight deviations could cause problems later. These measurements ensure only perfect cases advance to the next step. What makes these cases truly remarkable is their reusability. Unlike most components that contain explosions, brass cases can actually be collected, cleaned, and reloaded by careful hand loaders. This recyclability is built into their design. Another example of the ingenious engineering that goes into these seemingly simple objects. That recyclability of brass cases is impressive. But now, let's look at the smallest yet potentially most dangerous part of ammunition manufacturing. What happens in a room where workers handle explosives so sensitive that a simple static electricity discharge could trigger a catastrophic chain reaction? Welcome to the primer production line, where microscopic imperfections can mean the difference between a perfect shot and a useless click when you pull the trigger. Think about it. Every other component in ammunition can be flawless, but if that tiny primer fails to ignite, you're left with nothing but disappointment. This critical component might be small, but it's essentially a miniature explosive device that manufacturers must engineer to be sensitive enough to ignite when struck by the firing pin, yet stable enough to remain dormant during shipping or handling. Let's watch how these tiny powerhouses come together. The process starts with the creation of primer cups. Small metal containers typically made from copper or brass. These cups might look simple, but they're manufactured to incredibly precise dimensions to ensure proper fit in the cartridge case and perfect interaction with the firing pin. The next stage is where things get really interesting and dangerous. Inside these cups, workers carefully place the primary explosive compound called lead styphnate. At one facility I visited, a safety officer recounted how they once detected an abnormal static reading during a routine check. The entire production line was immediately halted until they identified a small tear in a worker's specialized footwear that had compromised the grounding system. Check out how the workers add the next component, the anvil. This small metal piece serves as a tripod anchor that ensures every spark finds its target. When the firing pin strikes the primer cup, it compresses the explosive compound against this anvil, creating the pressure and friction needed for ignition. The positioning must be perfect. Too high, and the primer might detonate too easily. Too low, and it might fail to ignite at all. The manufacturing area for primers looks completely different from the rest of the factory. It's physically separated and equipped with specialized ventilation systems. The floors are made with conductive materials connected to grounding systems, while workers wear special clothing and footwear designed to safely channel any static electricity away from the sensitive materials. Quality control here is absolutely critical. Each primer undergoes multiple inspections throughout manufacturing. Workers and automated systems check for proper assembly, correct compound distribution, and perfect anvil positioning. Think of it as inspecting thousands of miniature explosive devices, where even a microscopic flaw could lead to failure. Look at those testing stations where sample primers from each production batch get subjected to controlled strikes. The sophisticated equipment records not just whether the primer ignited, but exactly how much force was required. Differences measured in tiny grams of force that determine reliability in the field. The stakes are incredibly high in this part of the factory. A primer that's too sensitive could potentially detonate during shipping, while one that's not sensitive enough might fail when you need it most. Engineers walk this delicate line by implementing meticulous quality systems that ensure whether you're a hunter in the mountains or in a self-defense situation, that tiny primer will perform exactly as expected when you pull the trigger. While primers provide the initial spark, they're useless without something substantial to ignite. Moving from the primer assembly area to the propellant production facility feels like stepping from one danger zone into another, but with a crucial difference. Ever wonder why ammunition manufacturers shape their propellants into tiny cylinders, flakes, or balls instead of using actual powder? The answer reveals why a simple change in geometry can mean the difference between a controlled explosion and a catastrophic one. The term gunpowder might conjure images of fine black dust from old Western movies, but what we're looking at in this modern factory is completely different. Today's propellants are primarily made from nitrocellulose, a substance that starts as cotton before being chemically transformed into an energetic compound that generates massive pressure in milliseconds. In this section of the factory, massive mixing machines that look like industrial bakery equipment combine nitrocellulose with various stabilizers and performance additives. The mixture resembles a thick paste at this stage, nothing like the finished product you'd recognize inside a bullet cartridge. Now watch this paste transform. The mixture gets forced through specialized dies during extrusion, squeezing through tiny openings to create specific geometric shapes. Some emerge as tiny cylinders, others as flat discs, star shapes, or perfect spheres. Think of these shapes like different types of fuel in your car. Some burn fast for quick acceleration, others burn steadily for long-distance driving. See those cylindrical grains with different length to diameter ratios. The ones with more surface area burn faster, creating higher initial pressures. Perfect for shorter barrels. The ball-shaped propellants burn more progressively, making them ideal for heavier bullets needing sustained pressure. It's amazing how shape alone dramatically affects performance. These wet propellant particles need to dry completely in special temperature-controlled rooms. Imagine what could happen if even a tiny spark touched the invisible cloud of combustible particles floating in the air. Instant ignition, leading to potential disaster. Look at these workers with their specialized conductive footwear walking on conductive floors, all part of an elaborate grounding system preventing static electricity buildup. Along the ceiling and walls, specialized ventilation systems constantly remove potentially dangerous dust. Every electrical component, from lights to control panels, is explosion-proof, designed to contain any spark. Even transferring propellant between containers involves careful procedures to prevent friction and static buildup. The drying process sometimes takes days to complete, requiring constant monitoring for the perfect moisture level. Too much moisture, the propellant won't ignite reliably. Too little, it might become dangerously sensitive. This meticulous control ensures each batch meets exact specifications before moving to testing. Before leaving this section, each batch undergoes comprehensive testing in specialized laboratories. Technicians conduct chemical analysis to verify the propellant's burn rate, energy output, and stability. They're looking for exact specifications. A propellant burning too quickly creates unsafe pressures, while one burning too slowly might not achieve the desired velocity. Even slight variations affect accuracy or reliability. Check out this testing station where samples are burned in a controlled environment to measure pressure curves and burn rates. These detailed measurements ensure that when a shooter pulls the trigger, the propellant will ignite and burn at exactly the rate needed to safely propel the bullet to its intended velocity. No more, no less. The rigorous quality control connects directly to the real-world performance that shooters depend on for consistency and safety. Those burn rate tests are just the beginning of quality control. What's truly mind-blowing is how manufacturers can detect potentially dangerous ammunition without ever firing a single round. And it all comes down to a testing method that can spot defects smaller than a human hair. Now we're at the most exciting part of the factory, where all four components, primers, cases, propellants, and bullets, finally come together in a synchronized ballet of machinery. This assembly line represents the culmination of everything we've seen so far, with timing so precise it would make a Swiss watchmaker jealous. Look at how these cases are being loaded into high-speed machines for primer insertion. The machinery applies exactly the right amount of pressure, calibrated to within fractions of an ounce. This precision is crucial because applying excessive force could detonate the primers right on the assembly line. The cases then move to the powder dispensing station. These computerized dispensers measure out propellant with astonishing accuracy. See how each case receives its carefully measured charge. Even a variation of just a few granules could create a round that's either underpowered or potentially dangerous. The machine immediately verifies the weight after dispensing, automatically rejecting any charge that's even slightly off spec before moving to the next stage. This level of precision explains why modern ammunition is so much more consistent than what was produced even a few decades ago. The bullets are up next in this choreographed process. The machine seats each bullet into its case at a specific depth measured in thousandths of an inch, differences you literally cannot see with the naked eye. This measurement, called the overall length, affects everything from how reliably the cartridge feeds to the pressures generated when it fires. For certain ammunition types, especially those designed for semi-automatic weapons or hunting, watch how the machine compresses the case mouth around the bullet. This crimp holds the bullet firmly in place during handling and provides just the right amount of initial resistance when the propellant ignites, helping to build optimal pressure. Every step of this assembly process has multiple checkpoints. There are visual inspections happening both by automated cameras and trained quality control specialists. Each station verifies different aspects, from weight to dimensions to visual consistency, with nothing moving forward until it passes every test. Now check out the non-destructive testing station. This amazing technology can detect microscopic defects by measuring exactly how cases expand when subjected to controlled pressure. Even hairline cracks or material inconsistencies show up in these tests, allowing potentially dangerous rounds to be identified and removed before they ever leave the factory. The final station packages the completed ammunition into specialized trays designed specifically to protect those sensitive primers and maintain perfect alignment during transport and storage. The most premium ammunition even gets individual compartments to prevent bullets from touching each other, which could damage their carefully engineered tips. Take a look at the final quality control station, where samples from each production batch are test-fired to verify performance. The testers measure velocity, accuracy, and pressure curves to ensure everything matches the exact specifications for that particular ammunition type. If anything falls outside the acceptable parameters, the entire batch gets flagged for review. What we've witnessed throughout this journey isn't just about ammunition production, it's a story of innovation that transcends industries. From precision engineering to materials science, the meticulous quality control methods pioneered in ammunition manufacturing now influence critical safety systems in aerospace and automotive fields. Looking forward, ammunition technology continues its remarkable evolution. Today's bullets are crafted with the precision of fine watchmaking, engineered for specialized applications, while reflecting centuries of advancement in materials science and aerodynamics.